Cool. So we're going to be talking today about emulating IoT firmware and some IoT malware as well, using Docker and QEMU. A lot of this is stuff that you can do easily with old tools, but we're going to be checking out some new techniques. So just an overall view of what we're going to talk about and how it's going to look. First, I'm going to cover just some of the basics of emulation and containers and stuff to make sure that anybody who's not really that in the know on that side of technology isn't left completely dangling. We're going to talk about the multi-architecture container images that you can build using Docker and QEMU. That's going to be the main focus, and then we're going to do a couple of case studies of using these multi-architecture container image concepts to emulate some router firmware and also to emulate some IoT malware. So this is useful techniques for vulnerability researchers, exploit development, reverse engineering. It is also important for malware research so that you can actually study the runtime behavior of some kinds of botnets or whatever else is going around out there. Then finally, we're going to talk about the limitations of these techniques, but also the advantages that they carry along with them, and some ideas that I have for directors to go on more work and research. So what motivates this work? The main thing is that Docker is a really easy way to build and isolate processes, and it makes it also easy to share these images through registries. So you can build something on your workstation and get it figured out and then put it to some registry. Then your friends or other users, people who might want to take a look at your software, can just pull it down, and they don't need to configure their system or install any packages really. They just need to have Docker installed. They pull the image and they have your application. And if you've ever done work on like embedded firmware and and emulating weird stuff like routers with QEMU before, you know that it can be really time consuming. There's a lot of tools out there that kind of help you along with it, but a lot of those tools are also unmaintained and broken in some pretty important ways. There's a lot of overhead, just both in terms of the computational resources it takes on your system to run a full virtualized system. Like if you're imagining to actually run a whole botnet on a system and you have a bunch of VMs, those are going to consume a lot more resources than the same number of containers. So there's a lot less overhead when we are working with containers, and we can get a lot of valuable information out of firmware dumps or malware samples by looking at them in containers without going through any of the necessary complicated steps for setting up a virtualization lab with QEMU and KVM and libvirt or whatever. And we can also get quite a lot of useful information out of the samples that we have. Why are we particularly interested in the multi-arch images for IoT stuff? Because these IoT devices run on usually non-x86 platforms. Routers are usually MIPS. A lot of embedded devices out there are ARM. So we need to be able to easily run malware that is going to be targeting these kinds of devices in an environment that will natively execute them. And basically, attackers have a lot of advantage in this domain because there's a lot of vulnerable IoT devices out there. In order to research them, you have to do quite a lot of legwork to even get a lab environment set up. So not a lot of people are paying enough attention to IoT security, and the vendors generally don't really care that much about security. And even if they did, users rarely update the firmware. Like there's so many devices who updates their smart TV, right? So there's just a lot of room for improvement in this domain. So quick overview on Docker. Containers are basically a way for applications to be shipped in such a way that their entire runtime environments, library dependencies, configuration, etc., are bundled within the application itself. A lot of people call them lightweight VMs, but it's kind of misleading because there's not really any virtualization. They're using kernel features like namespaces and C groups to implement the functionality of process isolation and resource constraints. If you look at a lot of GitHub projects, you probably see Docker files around out there. I assume most people who are listening have worked with Docker before, but basically the image is built from a Docker file, and we're going to be seeing a few examples of Docker files later on, so that's why I'm bringing it up. This is basically just a set of instructions that Docker executes to build a file system image for your container. So this is how you specify all the steps that are necessary to build your container. And then once it's built, it's built. And a container is just a stateful instantiation of a container image. And these container images are composed in layers. So you can easily customize them. You can imagine a base layer that is just like Debian, and then you maybe install Nginx and configure some vhosts on it. Then you can publish that as your own image, which it's your Debian web server. And so now voila, you have a custom Debian web server image. So this is a basic invocation of using a Docker image. And this first one, I'm just saying start a bash shell on Debian stable. And I cat the etc Debian version 9.9, great, okay. That's not my Debian version on the local host. And this one, it's a sneak peek at what the multi-arch images are capable of. I'm doing basically the same thing, running the uname-m command on the MIPS version of Debian, like minimal Debian chroot, and voila, it prints me MIPS. So this container thinks that it's got a MIPS processor, even though really it's an x86 machine. So how does it do that? Well, it's because of QEMU, and QEMU is a generic open source machine emulator. So you've probably seen or worked with QEMU before if you've done any kind of work on firmware or embedded devices. Typically, this is going to run in environments where it is on top of like KVM and it's being managed through libvirt. Again, like if you've worked on an OpenStack cluster or any kind of cloud, really, most of those things under the hood is just QEMU, KVM, managed by libvirt. So this is the full system emulation mode, which emulates the entire operating system from the kernel up. And this is the use case that I think most people would probably be familiar with. But QEMU has also a completely separate mode that it runs in, where it is completely userland tools. And this user space emulation is really useful for our purposes, because one of the things we're trying to avoid in this work is the overhead involved with having to boot the whole kernel, having to also know details about the kernel from the firmware that we've extracted. And we just want a quick and easy way to ship that file system and any binaries that are going to be running on it. So this actually fits our use case beautifully, and it goes along with Docker incredibly well. So how does this work? Basically, it is translating the CPU instructions on the fly. There's and it will also emulate the syscalls on the fly. So you can imagine how this works. It's inside the container, there is a MIPS instruction, but this MIPS instruction is being run underneath a shim of QEMU, and this QEMU is able to take that MIPS instruction, translate it to the x86 instruction, or take it from the guest syscall into the host syscall. It is important to note, though, that not every system call can be translated or is implemented in one of the QEMU interpreters. There are if you run through any of these on your own, you'll see when you run the init scripts, for example, a lot of failed syscall errors come out. It doesn't actually end up seemingly affecting any change on how things run, as we'll see later. But there are some syscalls that either the container isn't going to have enough privilege to invoke on the host, or that QEMU just simply doesn't emulate for one reason or another. A lot of that revolves around signal trapping and signal handling, because since the container doesn't have its own kernel, it is relying on the host kernel to do stuff like signal trapping. So anyway, long story short, you're able to use these QEMU emulators to seamlessly run a non-native binary on your x86 workstation. So how does this work? There is, under your file system, pros sys fs bin format misc, I guess is how we're going to pronounce this. There's a way to register interpreters for a particular ELF signature. So what this means is when the operating system is looking at a ELF that you're trying to execute, it's going to read this magic number. It's going to consult this bin format table. Do I have some particular interpreter that is registered for invoking this? And if it does, then it will use that interpreter. And like, it's going to seamlessly do this. Like if you have just on your local host, like a crop a.out, and that's compiled for MIPS, and you've registered on your local host a MIPS interpreter for that ELF signature, then when you execute that that file, just at like /a.out, it'll run, because the QEMU interpreter is just sort of silently being invoked when you run that. And you'll see how this looks actually in the PS output that's going to be in some of the slides later. So now we're ready to talk fully, I think, about the multi-architecture containers, container images for Docker and QEMU. So the first thing that you have to do, and this is sort of unusual for Docker containers to have to require any other software being installed on the host system, or to run a command in privileged mode before you can actually use it. So I know this is a bit weird, but it's actually necessary, and it works surprisingly well. You could do this on your own if you're freaked out about running someone's code in privileged mode, but if you look at how that stuff works, it's both really enlightening as to how this whole bin format registry works as a whole. But basically, to do this, we need to install QEMU on the host system, and then we will run this privileged QEMU user static command. So this is pulling an image from the multi-arch repository on Git on Docker Hub. It's gonna delete it when it's done running. It's passing the reset flag and the persistent flag. And so what this does is it populates all of these interpreters in that directory there. And the contents of those look like, if it's enabled or not, what the interpreter is, any flags to put in, any offsets to take into consideration, and the magic number is registered for, and I'm not sure what the mask value does. But this command is what gives you that. And it has to run in privileged mode because it has to change these files on the host operating system. And that's all it does. So like I said, you could just run that script actually on your own host system, but this is important for the containers to know. It's important for this container to be on the system, because you have to be able to copy binaries out of it later on. And so once we've executed this command, we can test it out. So here's a quick and easy command to test it out. You just pull that ARM ARM v8 Ubuntu image and check the uname, and indeed it thinks that it's a ARM processor. So the basic use cases for this is seamlessly executing ARM, MIPS, PowerPC, any other random non-x86 binary you can think of. Like you saw that whole list, it's pretty huge, the number of emulators that exist in the QEMU universe. If you were interested in, say, reverse engineering malware, or even reverse engineering a binary blob component of a router or an IoT device, you could set up your container image to also run a GDB server. So then you could do remote debugging on whatever programs are running inside that container. You can also feasibly connect a tool like IDA to decompile and patch binaries on the fly, just keeping in mind that once you've modified binaries, and I think in a lot of cases it's going to be necessary to get them to actually work, that there are some parts of binaries in the init scripts of these routers that I've looked at where definitely if you want to avoid some serious errors, you will probably have to take out some bits of some instructions. But then you're not really studying the same system, you're studying a different system. So that's one limitation to keep in mind. We're doing a lot of things that are changing the complete environment of how these systems are intended to run. And we have to always keep that in mind, that we're not really working on the device itself, we're working on a really packed up emulator version of how that device is going to work. This is also a good way to quickly test out given payloads. So if you're doing some kind of local exploit development and you're like writing some assembly for ARM or MIPS and need to test it out, well, you can use this container to seamlessly execute that binary, just like we did with the uname-n command earlier. Excuse me. This is also particularly useful if you're porting something from a different architecture. If you want to make sure that, say you have a nice piece of shell code for ARM and you want to, as an exercise, port it to MIPS, then you have a pretty quick development cycle where you can test it out right away. So now we'll talk about how we can use these multi-edge containers to emulate the IoT firmware. And by IoT firmware, the only ones we're going to talk about are just a couple of routers, these guys right here. You could feasibly do this with other IoT devices. I just haven't had much of an opportunity to either get anything that's an interesting one or find one that has the right kind of squash file system that Firmadyne knows how to extract. So if anybody wants to try this at home and has a more interesting device than a router and gets it to work, I'd be really interested to hear about that. Nevertheless, getting firmware can prove a challenge. A lot of the times when you're lucky, and for these guys that is the case, it's a simple matter of just downloading from the vendor's website. And Firmadyne, which is a tool we'll take a look at in a minute, contains its own scraper module that will just pull down a ton of zip files from all kinds of different hardware providers. Not all of the files that it pulls down are useful in any kind of way. So, so it's a lot of signal to noise ratio, or a lot of, noise to signal ratio is very high. But those scrapers are pretty cool. And if there's some kind of exotic device that you're looking for and you can't find the firmware publicly, you'll have to get creative. I think there's other talks about that. But for our case, we're just going to look at this kind of popular netgear router that has a lot of known vulnerabilities, and a dlink dir 866, which also has some vulnerabilities. And I just simply downloaded these guys from the vendor. So Firmadyne is a tool that I use for extracting file system contents from the firmware blobs that I download. In the case of the netgear one, it was a zip file that I downloaded. And in the case of the dlink one, it was a bin file that I downloaded. Firmadyne knows how to deal with both. I just pass it in there and it extracts me the root FS. You could keep going down, like using only the Firmadyne tools to emulate this device if you wanted to. It has that capacity, but that's not our goal. So that would be a completely different talk. There's good tutorials out there if you want to do that. There are some advantages to emulating the firmware with full system emulation, but we want to do something else. So all we need Firmadyne here for to do with Firmadyne here is extract the root FS. And you can see like this is all that's necessary to do. I'm running this inside of a Firmadyne container because even Firmadyne has a container. Very straightforward command here. You just pass it the file name and tell it to unzip to the images file. You can see it does some work, and then voila, we have in this images directory one.tar.gz, which I'll rename back to netgear wnap 320.tar.gz. Then this is the Docker file for turning that tarball that we just got out of Firmadyne into a Docker container image. So this first stanza is just instantiating that we want to call multi-arch Debian Deb Bootstrap MIPS Buster Slim. So this is just a minimal Debian image that has the MIPS emulators on it. And we're importing this as QEMU. This is like a Python import statement, basically. We do absolutely nothing with it. Then our next step is a completely new container that we're talking about that is starting from scratch. And scratch means nothing. It is just the bare minimum like process file system and stuff that it mounts from the host operating system. We add the contents of this firmware.tar.gz, which is the bundle we downloaded or extracted from Firmadyne. We copy from this QEMU template just the file QEMU MIPS static, and we throw it into user.bin. Then we tell Docker that you prefix commands with QEMU MIPS static bin busybox. Then we export the environment architecture to MIPS, and we're done. That's it. Very, very simple. This is the build, what it looks like. Happens really fast. We just copy over that binary. If anyone is going to follow along with this, like as a tutorial or whatever, one thing to keep in mind: this is a bug in the registrations in the multi-arch registration scripts, where it registers both the QEMU MIPS and QEMU MIPS N32 and N32 EL, which are just like slightly different variations, but they will seg fault if you try to execute a regular MIPS binary on them, but they have the same magic number. So there's the QEMU MIPS and then QEMU MIPS M32 are registered the same thing. So you just disable those by echoing -1 into them as root, and then they go away, and then all of your MIPS images will run fine. This was a major stumbling block, and it's not very easy to find out about. So I thought it would be good to include it here. So now let's explore the new shells. So I did the exact same build process for both the netgear and the dlink router that we're going to be looking at. The only difference was the contents of the firmware tarball. So they have the exact same Docker file. They just live in different directories, and those directories is different contents in firmware.tar.gz. So let's run this and see what's up in the shell. We see there's this Linux RC file in the root directory that looks interesting, but it actually just points back to bin busybox. Kind of weird. We can see what binaries there are. There's some kind of interesting looking ones. Some interesting stuff in the etc folder. There's this weird admin user that has its own shell. And then this shell's got some weird stuff in the path. Be interesting to look at some of these things, firmware upgrade, password, etc. And we can also see all of the init streams that it goes through. And that tells us a lot about how the system comes up. And that also tells us a lot about how to improve this image such that when you start it, instead of just spawning a shell, it actually starts the whole init service without failing. And I'll talk more about that later. And let's explore the web interface now. Like this works too. We're exposing my localhost port 8080 onto the container port 80. So if I just pull up my browser, point it at the server that this is running on, I see this beautiful netgear router page that mostly functions. And this is after all the init scripts have run. Like I said, these init scripts contain a ton of errors just because of the limitations that we'll discuss in detail at the end. But really, most of the important services are running, and you can see you get a good idea of what's going on inside that router without having to really do much work if you just pull this image and run it locally. So this is the dlink router. We can take a look at that too. And I have shells open on all these in another tab. So if there's time left over at the end and anyone wants to take a look at what's in those things, we could take a dig in more detail. So this is the dlink router. It's actually quite a bit different. The stuff it's got in the sbin and bin. You can see that etc services is just a ton of PHP files. Some of them have kind of insane sounding names. There's a lot of interesting stuff inside these file systems. I really wonder what is FW sign, build rev, image sign. There's random PIM files in here. There's so many things to explore in here that are inaccessible unless you're willing to go through the full process of setting up a QEMU environment to emulate it. And since this process is more or less just the same for each one, as long as we're able to extract a tarball from Firmadyne, you'd be able to feasibly use this process to build a ton of images with complete automation and find all kinds of crazy shit inside of routers that probably nobody's even looked at or like properly given a full audit on at least. So now we're going to move on to the next topic, which is emulating the IoT malware with Docker. And the case study here is going to be the Mirai botnet. And there's a variety of reasons why this botnet is of particular interest for these techniques, because it primarily targets IoT devices like smart TVs, security cameras, personal home routers, you name it, all kinds of things that are just out there running Linux and probably never seeing a patch ever. Also usually with default settings. At some point in 2016, some researchers finally discovered it and made a release about it. A few months later, some person claiming to be the author releases the full source code on hack forums, and as a result, a lot more people started using it. Many new different variants of it emerged. Most of them, I'm gonna guess, are just people rebranding the splash image or doing something stupid. But some of them might actually have completely different functionality or capabilities. I think there's archives around of quite a lot of different samples. And again, with these techniques, I've only built one Mirai variant, but it's feasible that with a few scripts, you could again set up an automated pipeline for getting Docker images that have all of these Mirai variants at least compiled. Most of the devices, of course, are not going to be running x86 processors, routers, and these other smart TVs, usually MIPS or ARM. And since this hack for is the source code is in the public domain, so we can just build this ourselves and change whatever we need to change to make it safe and sane to use. And here's a quote from the hack forums post. With Mirai, I usually pull max 380K bots from Telnet alone. This is this is how they talk. It's kind of funny, but it's also it tells the extent of how crazy this is, because there's so many things out there with open telnet and default credentials, and I believe this crazy brag because 380,000 in October 2016. Things have improved a little bit since then. That seems feasible, and like that's a lot of bots. That's a lot of things out there running this malware that can potentially be pretty destructive, and it was responsible for some of the largest denial of service attacks that we've seen. So this is to highlight the severity of why this IoT malware is so important to research and understand, and also why it's sort of like quite a joke. So how is this botnet structured in terms of the source? So basically divided up between the command and control server and the bots, which are the clients. The command and control is written in Go, and the bots are written in C. If you look at the stupid hack forums or other like places where skids talk about booting and stuff, one of the recurring themes among them is not knowing how to use GCC. Like the build instructions for the stuff that it comes with is pretty leaves a lot to be desired. There's no make file. There's no there's no effort was made to ensure that this stuff compiles or builds in any kind of way that's reproducible or reliable, because obviously they're malware authors. You know, they're trying to make a buck, not really make a beautiful build pipeline for their software. But through a process of trial and error, I was able to figure out how all of these stuff is supposed to be configured, and figure out which of the variety of like hard-coded values you need to override that are not described in the original blog post or the hack forums post that came along with it. Figuring out how this stuff is actually meant to be compiled, and then being able to build it in a way that's reproducible when you're trying to modify it or see what certain pieces of code are really supposed to do, would be kind of a pain without these Docker built containers. So this is why I think this technique has proven really valuable for researching this botnet in particular. And this code base is really just like, it's infuriating to follow. So much of it is just extremely sloppy and confusing. But some of it is really funny, like this anti-GDB entry thing. I have no idea what that's supposed to do, but some lame attempt at anti-forensics from me is just a joke. I don't know, but there's a lot of just bizarre stuff in there, which makes it kind of a nightmare to modify this stuff, because and you do have to modify it in order to get it to run for you, because the IP address that is going to be listening on and the IP address that the bot thinks that the C2 is going to be on, these are all compiled these are all determined at compile time for the bot. So you have to go digging through the source. You have to find out where these things are defined. You also have to see what else it is doing. So when I ran this for the first time and actually got it running, I was so excited. And then I started seeing like target IP addresses, some IP address that is not in my local network. And I'm like, holy shit, this thing is actually going to start trying to brute force telnets. I'm going to be pulling 380K bots a day soon. So I shut it off and then dug around in the source, finds out that it has this get random IP function, which hilariously just generates a random IP address and then makes sure that the octal values are not contained in any ranges belonging to like the US Postal Service or the Department of Defense. So it has some of these sitter blocks that it ignores, and but then when it just gets a random IP and it scans it. So once this bot starts running, it's going to start scanning and attacking anything that's got a brute forceable telnet or whatever else it's looking for. And this is one of the valuable things about running it, is you get to see exactly what it's looking for, and you get to see what it does when it finds something that it thinks it might be able to attack. So a lot of customizations had to go into the Mirai source to really get this working. And I basically neutered the thing by making sure that the only subnet that is going to scan is in this 172.30.30 sitter block, which we'll see later is the sitter block for targets in the in my Docker network that I set up. And this is just another look at the Mirai source code. So this is how the whole tree looks. It's not super surprising. There's the bot, it has a few files. Main.c is obviously the entry point. Then the C2, there's the Go files for it. The thing that I did to make this easy to build is I wrote a little shell scripts that just compiles the bots in a reliable, reproducible way. And then I added a make file so that I can just issue a simple command that will build all those things and put them in the directory that I want them to go into for the container to build. So the important thing to understand is the source, for the absolute most part, except for the couple of files that I had to make changes in, is the same as the original source. And all I've added is just a couple of scripts to make my life easier that will be executed inside of the Docker container, the build container. So this make file is not executed like on your local host. This is supposed to be executed inside the container. This is for building Mirai in a way that is not running a bunch of long one-line commands. And this is just an example of my fixed up get random IP function. The original thing that they had in here was absolutely shameful. So this is how it was. This is basically the most significant modification that was made to the source. Almost everything else is the same. So now this is how the Mirai's interface looks. Once it is up and running, you just telnet to the local host. It's listening on some port. It's usually something stupid. The username and password you set in the database as root. You get the stupid splash screen, and then you count your bots. So it gives you a whole variety of attacks that you can send to your Minecraft enemies, and a bunch of flags that, frankly, I've just looked at this briefly, but it seems kind of interesting, but I'm not really sure what the use for all this crazy stuff is. Anyway, all that stuff is implemented in attack.c. So if you're interested in all of these different DDoS techniques that are built into Mirai, attack.c is the place to look. So here's our build image Dockerfile. Like I said, the tool chain for building this whole thing is kind of complex. You have to have Go installed, I think a particular version. You have to have a bunch of cross compilers installed on your system and in a particular file system path. You have to have basically a lot of setup on your local machine that maybe you don't want to bother with, or maybe you don't want to pollute all your local machine with a bunch of cross compilers just to build this malware. And also you probably don't want to run the malware directly on the local machine. Some kind of process isolation is nice, even though Docker isn't super secure for, it's possible to escape a container. So we can see basically it installs Go, creates a user for Mirai, copies over some scripts that just download the cross compilers inside the container, executes these cross compilers, runs a make command, and then spawns a shell. So most important thing is, I guess, that it's putting all the stuff that it builds into the /build/Mirai/release directory, because we want to be able to copy all those compiled files that we get out of this container into the container images that we're going to use for actually running the C2 and actually running a test bot. So this is the Dockerfile for building the C2 image. Basically, it is going to, this one is based again on just Debian stable, minimalistic, installs and configures a MySQL server, create some directories for serving those bots. So whenever it scans something that needs to be attacked, and the payload is supposed to actually download the bot so that the new machine is recruited to the botnet, it's getting them from a web server or an FTP server that is running on a C2. And so yeah, basically we just copy over all of the bots into those directories where we're going to serve them from. And we copy over the compiled binaries from the build box to the C2 box. We also add a little script for provisioning the database. We expose port 22 so we can SSH to it, and we expose the joke port that the C2 is listening on for telnet. The bot image is pretty much the same. That this just provisions a minimal Debian container that has the bot already on it, so we can test, that the C2 and the bot are actually making a connection, and we can also study the behavior of the bot when it's running on the system, see what kind of things it does. We could attach a debugger, we could strace it, any Debian package that we want to install. We could just install right in that container to do whatever kind of debugging or analysis on that bot while it's running, just like on the same machine. So this Ansible stuff completely ignored. That's for something else. That's for something completely unrelated to this talk. And yeah, basically we are building here just a minimal Debian machine with the Mirai bot on it that is on the ARM processor. And this is what it looks like when we have our minimal proof of concept put together. This is inside the C2 container. I start the control. I see the splash screen. I'm just sitting here now reading the std error, and I see, hey, a bot connected. It gives me its IP address and the remote port it's listening on. Great. And inside the bot container, I'm seeing, yep, it's attempting to connect. It tells me the CMC's IP address, and boom, yes, I'm connected. So voila, we have a Mirai C2 and a Mirai bot that are talking to each other through Docker containers. Now we can put all of this together to build a botnet in a box. We can set up a Docker Compose script that will bring up our C2, bring up our test bots if we want them to. It can bring up any of the vulnerable targets that we've built and configured. So you can see I'm just running here make start on the Docker Compose file that just exposes the services and statically assigns IP addresses. And we can see, yep, the C2 is running, the bot is up there, the vulnerable targets are up and running, and I have an Ansible control node that I can use to change configuration on these things on the fly. So the advantages for these techniques are that we can easily explore the contents of a wide variety of IoT devices with relatively low overhead. We can rapidly prototype exploits for a variety of CPU architectures, and we can see how their runtime behavior inside of an isolated process environment. We have a lot of opportunities for automation because one of the big advantages of using stuff like Docker and containers is that these tools fit in nicely with overall like bigger automation pipelines and deployment pipelines. So you could even, for example, conceivably do a botnet test lab as a service. If, for example, you could figure out how to get this up running on Kubernetes. Most importantly, though, we can share these images. So instead of having to follow through some old blog posts or rely on old notes, unless you're somebody who is emulating new firmwares every day and know QEMU's obscure command line flags by heart, it's a painful process to start digging into something like this. Whereas what we have here, you can Docker pull whatever router I'm interested in, and then you have a shell on it, and you can even get it running a web server. So the ultimate goal of this work is to make IoT research more accessible and more efficient. So drawbacks are pretty significant as well, though. One of the problems, like as mentioned before, we can't emulate a lot of syscalls. This causes sometimes unexpected behavior, and it makes it such that we're working on a different system than the real system that's running on the hardware, and that can be meaningful to some kinds of research, and to other kinds of research it isn't. So it's just something to always be aware of and to always keep in your mind when you're changing the state of a system, or when you're modifying the contents of a binary. It's no longer the same thing that it was before you modified it. So things may be completely different. Small changes can make big ramifications. Another big problem is a lot of these routers store important configuration data in their NVRAM, which obviously the container doesn't have, and your host kernel doesn't have. So this makes some router and its scripts completely fail, and there'd be no way. There's like a Huawei router I was looking at, and if it can't read anything from NVRAM, it doesn't even know what its IP address is, and it just dies immediately. So that's an example of a router that if you wanted to get it fully working under this technique, you would need to do some kind of binary mangling on the init script itself, so that it doesn't try to look up these NVRAM values. Or alternatively, you could do an LD preload trick and make your own little get NVRAM utility library. This is something that NVRAM Faker is a project on GitHub does for ARM. I don't think there's a MIPS version of it, but or maybe the other way around. But anyway, you could do an LD preload technique to fake calls to NVRAM, but you would still need to know the values of things that it expects to get from NVRAM, and you would need to know what fake values to put in that store to return when the router actually wants it. So there's a lot of guesswork involved and a lot of trial and error involved with getting certain kinds of devices to work, especially when they're relying on other peripherals that are hardware that you don't have and that you're not emulating. Also, kernel exploits are not going to work. So if you're hoping to do something on a router and part of your chain is a kernel exploit, then you're out of luck, because you're going to be exploiting the host kernel, and it's probably going to not be the version of the kernel you're hoping it is. So if you want to test kernel exploits on these things, you need to use QEMU. But for the most part, we're interested in just examining the structure and the contents of these things, doing binary analysis on these things, seeing how they run, seeing opportunities for authentication bypasses. You can find out a lot of information just by reading the files, seeing what the contents are, and running through some things like a firmware update and just watching exactly what it does. And one of the other final drawbacks worth mentioning is that a lot of the tools that we depend on here are have major bugs and they're not very actively maintained. Like Firmadyne scrapers, some of them are great and some of them don't work at all. Like the domains have changed completely and they haven't seen an update in a long time. And also there was that registration bug with the multi-arch container that I mentioned earlier. And there's an open issue on GitHub for it for like 2 years, so it hasn't been addressed either. Some ideas for further research. I mentioned the LD prelude tricks for working around the NVRAM limitations. I would love to see this applied to other kinds of IoT devices. Would like to get my hands on some firmware that I can emulate. And also building debug versions of these container images so that we can get a GDB server running on them. And finally, like making a completely automated workflow on these things so that we can go from a scraper to the rootfs extractor to the image build and just have a massive pipeline on it. So thank you, and I'm ready to answer any questions. Also, if you have anything that you want to email me about, that's my email address.
Yo, that was sick.
Thanks.
Yeah, that was a really awesome talk. I'm very happy to see how it all came together. Hold on, let me close my window here. It's loud. Yeah, that came together really well.
Cool, thanks.
So yeah, I guess like, I don't know, do you have any quick question? How long did it take you to figure all of this out? Is someone said in the chat.
Yeah, so this is a few months of work in my free time. Yeah, and also I have shells open on all this stuff. So if anybody wants to see a look at anything, I've got right here. This is the C2. I've got it connected. This is my dlink router. This is my netgear router that's running the whole system. That went through the whole init process.
Yeah.
And I also have the web UI up on my Amazon server. I might drop the link to that later so people can take a look at it. So if there's anything people want to see, let me know.
How far have you scaled it? Like how many port connections?
So I mean I could feasibly do as many as like the machine that it's running on would be able to tolerate. I haven't gotten anywhere near 380K, if that's what you're asking. The main thing I'm interested in is just getting these things to communicate. So adding the scale would be, just a matter of adding more things to the Docker Composer, adding more replicas.
This has a question in the chat, is too. Have you considered setting up a Mirai honeypot to catch fresh versions of stuff? And then building on that, have you considered creating a honeypot for doing botnet takeovers? You don't have to answer.
No, I have not considered that, but now that you mention it, maybe I will.
We've seen there's a very funny what's it called? Buffer overflow in the C2 port. Look at NetSpoopy's Twitter.
Oh yeah, I know about that. We can test that here.
But yeah.
Is it still open now? It's an out of index, right?
Yeah, there's like a very small buffer for what's it called? The login port.
I got it. I just made the bot start scanning, so you can see it's going over my whole subnet. There's nothing there for it right now because I got this together really quickly. Basically, I put this whole thing together last night. The server that I had all this research on originally was destroyed, so I had to start over basically from scratch. But yeah, bots won.
That's impressive though that you can spin it up and down so quickly. Like now that you've done the work.
Yeah.
So another question too. Is there any GitHub repo to download any of your code?
No, but I think some of it I'll try to release in the near future.
Okay.
Like a lot of the stuff especially with the Mirai stuff, I was hesitant to release because I don't really want to give like a blueprint out for making your own Docker Mirai C2s. But the stuff on the router firmwares, I feel comfortable sharing because that's just building the router firmware.
Yeah.
So yeah, I'll probably release something and maybe we can get that link out on Twitter or something in the future if that's done. I would like to release this stuff as much as this is possible. I would like to release, yeah.
Oh yeah.
You should
That's awesome.
give a copy to Andrew Morris from Grey Nose so that he can have hella booters.
Yes. That's Andrew
So
Moore.
Ilya, you haven't. We didn't share any of your contact details previously.
Mm-hmm.
You didn't fill them out. Is there?
Yeah,
anything
that
you'd
was
like
by
to follow?
design. Hmm?
Yeah, sure. We understand. But if there's nothing you wanted to share with anyone to go look at, anything you wanted to spruik?
Yeah, well, my email address is in the end here. You can hit me up there. I'm on Matrix. I'm on IRC. Draw me a line, and I'll find a way to get in touch with you. And also there's I will make some of this available on GitHub soon.
All right, cool. Yeah, we'll make sure that we can. Well, if you guys follow at AirGapin on Twitter, any sort of slides or anything that you are looking for, any code, if we do get it, we will tweet it out from there. So at AirGapin on Twitter.
Yeah.
If you already follow ThugCrowd, it's probably you get it from there.
Yeah, you'll probably
so.
you'll probably find that too. But yeah, that's just the fastest way to do it.
Right.
Skellstick asks for your full name and address.
Skellstick's gonna try and poach you.
So yeah, thanks Ilya for coming on and talking with us. This is awesome. We have up next MG.
Whoa.
Cool. Yeah, excited for that. All right, thanks guys, and thanks to everyone who contributed to this as well. A lot of you guys are involved with this. A lot of people from Matrix are involved. So yeah, thanks to everyone, and take care.
Thank you.
Thanks, man. We'll see you on the Matrix.
Yep, I just need to figure out how to exit this shit. Okay, bye.
Bye. So yeah, MG will be on here. He is going to be talking about rapid prototype